This presentation on Joule heating was prepared by Sam Williams and Sean Tingey for a 423 ME heat transfer project. First, we wanted to talk a little bit about what Joule heating is and why we care about it. Joule heating is only briefly mentioned in the textbook. It's electrical resistance heating, and it is equal to the power through the device. The two techniques used are chromatography and electrophoresis, and they're used to separate different molecules in your solution, and it does that based on the polarity for chromatography and the charge for electrophoresis. Now, Joule heating is known to cause inaccurate results in these experiments due to the changes in viscosity due to local changes in temperature. So our purposes are to mitigate or avoid Joule heating altogether.
We'll first describe what electrophoresis and chromatography are. Electrophoresis is the technique used in laboratories in order to separate macromolecules based on size. The technique applies a negative charge so that proteins move towards a positive charge. The front view shown shows two small holes in the back of the bottom plate. These are where the electrodes are inserted to induce a charge. Chromatography, on the other hand, is a method for separating compounds so that what they consist of can be discovered. The front view also shows one small hole in the middle, which is where the solution in question is inserted. The back view shows where the thermocouples are inserted in order to track the temperature change across the thin silica plate where the solution is spread. These two images show the device being used in the chemistry department. The image on the left shows the two acrylic plates machined on the mill with the previously mentioned features and the thin silica plate between them. The solution is about to be added. The image on the right shows the power regulator, which applies 500 volts at an extremely low current. This device allows us to know our exact power input. The temperatures are also recorded across the plate to aid in our calculations.
This graph shows the calculated maximum steady state temperature increase calculations that we did using Mathematica. You can see we solved it for the delta T term, and we divide the Q in by 2 because this is 2 dimensions going through the upper and lower plates of the device. Now, the limitations of this graph is it doesn't show us how long it takes to reach steady state. Now you can see that the maximum power input that we graph here, 10, corresponds to close to 200. So that tells us we still don't know how long, but we know that it can cause problems and there is a drastic temperature increase. These are the transient calculations that we did to try to understand how long the device would take to reach those steady state temperatures. Now our time input here is 600 seconds or 10 minutes. Our power input is 5 watts. That's assuming the device is running 10, but it's 5 through the top plate, 5 through the bottom plate. That's how we analyzed it. So this one we tried to graph it, but we weren't able to get Mathematica to solve for ERF-C, so we just have one point here. So with 5 watts input, 10 minutes for the time, we're getting a delta T of much less than 1.
This graph shows the temperature results gathered from the thermocouples over a little more than 2.5 minutes. At this point in time, the temperatures have clearly not yet reached steady state, though a constant 5-watt source is applied. The graph appears to be a step function, which is still under question. Can you think of which type of trend the data should show over time? That's right. At a 5-minute span, you can more clearly see how the temperature begins to level off as it approaches its steady state. Under closer observation, it is assumed that the unexpected step function appearance of the data may be a result of the intervals between readings of the thermocouples or other factors related to how the readings were taken. At greater time spans, the graph shows its obvious true trends.
Alright, so the transient results we see clearly are not correct. We can see that the data shows that we have an increase of somewhere in the department of 1 degree a minute at least, whereas the transient calculations say that if we run it at 5 watts for 10 minutes, we'll only get a temperature increase of much less than 1, so those aren't correct. looking at the slope, we can see there's only a slight decrease in slope over the course of the measured data, so it probably takes a long time to reach steady state. And then the steady state temperature calculations show a steady state temperature much higher than ours, so our results are plausible. So looking at the data, we see that there clearly is an increase, and it is significant. Therefore, Joule heating is probably hurting our results. So we looked at some different ways we could decrease Joule heating. If we made the plates thinner, it looks like we could, based upon this equation, decrease the delta T by 25%. Now, if we use a more thermally conductive plastic, changing the K value there, we could decrease it by about 20%. And also, they tried cooling the liquid before injecting it into the device, but the volume is so small that's negligible. Suggested further research would focus on transient analysis of the Joule heating. If we can find out exactly how long it takes and be able to calculate that based upon the power input, then when researchers are using these devices, then they can calculate beforehand how long they can run it to be able to be sure significant Joule heating effects do not occur. We also can try implementing a thinner plate and try using more thermally conductive plastic. And we also want to run the device long enough that it actually reaches steady state to be able to see if those calculations were correct.